We now come to the idea of complementarity. Where does the whole concept of complementarity begin, though? It's important, firstly, to look at the example of experimentation upon a system, and the issues that surround it. Firstly, Bohr noted that there is no way to uniquely define the boundary between the system being measured and the system making that measurement. There is a division between the two, and this is famously known as the Heisenberg cut. The main issue comes with trying to determine what counts as the system being measured and the system making the measurement. For example, in the experiment of a photon hitting a detector screen, one could state that it's simply the photon that is the measured system. However, it's not too much of a leap to also claim that the detector is also part of the measured system, as we are in fact using other apparatus to observe this detector. How far could you go with this? Does the mind of the experimenter also count as the measured system? In complementarity, one looks only at a quantity in the example of an experiment where information related to that quantity can be obtained. One can look at the example of the measurement of position. Whilst a measurement of position could be obtained in an experiment, the conditions required for a precise measurement would lead to a very imprecise measurement for momentum. In this sense, only information about the position can be obtained. There are two basic ideas in complementarity: the idea of mutual exclusiveness and also of joint completion. Mutual exclusiveness tells us that in the example of position and momentum, measuring one of them will put limitations upon the other. Joint completion, however, indicates the way in which we can ultimately consider the two observables together, and that they provide a full description of a particle being measured. One can also see the example of complementarity in the measurement of angular momentum within a quantum system. The angular momentum can be split into three separate components. These components correspond to the x, y, and z directions. We know that the angular momentum is equal to r times by p. If we were to take the determinant of r cross p, this would give us an angular momentum in the z direction of ypz minus zpy. For the angular momentum in the y direction, we would get zpx minus xpz, and for the angular momentum in the z direction, we would get xpy minus ypx. It's possible to try and take the commutator of, for example, lx and ly. However, it can be seen that these do not commute. They do not give an answer of 0. However, it's possible to take any one of these angular momentums in a certain direction with the total angular momentum. This does in fact commute. Another important aspect of Bohr's interpretation is known as wholeness. In this, Bohr essentially stated the fact that the measured system and the measuring system can be considered to be linked. This was a response to the famous EPR paper of 1935. Whilst Bohr managed to amass a large amount of disciples to his cause, there are many issues with the Copenhagen interpretation that have to be noted. Firstly was the question of Bohr's theory of the way in which the act of measurement could cause a disturbance. Indeed, this originally provides a useful physical description for quantum theory. However, in the 1935 paper, the EPR paper, Einstein, Podolsky, and Rosen exposed the problem with this idea. In their paper, the physicists pictured an entangled system and asked what would happen if a measurement was made on one of the parts of this system. We can imagine two electrons which are in a superposition of spin up and spin down states. Spin up is indicated by an upwards arrow, whereas spin down is indicated by a downwards arrow. These electrons could be put into boxes, for example, and brought to opposite sides of the universe. One could then go ahead and make a measurement of the spin of one of these electrons. Due to the conservation of angular momentum, and the fact that the electron can only have spin up or spin down, whatever the spin measured for one electron, the spin of the other must be the opposite. The shocking thing here is the collapse of the second electron into the opposite spin state happens instantaneously after measurement of the other electron. Indeed, it seems that the change happens in less time than it would take light to go from one electron to the other. This indicates somehow that the information of the spin state of the measured electron has been transmitted from one electron to the other faster than the speed of light, the universal speed limit. This caused large problems for Bohr's view of the act of measurement, and he was forced to back down somewhat from his original view on the matter. His response in part came with the creation of this concept of wholeness.